So first off, I'd like to say welcome everyone to today's webinar. My name is Elise Roberts, and I'm with the section on statistics in defense and national security. I'm very pleased to welcome our speaker, Dr. Devin Francom. Dr. Francom is a member of the Statistical Sciences Group at Los Alamos National Laboratory. He received his PhD in statistics and applied mathematics from the University of California, Santa Cruz. His work is motivated by applications to quantifying uncertainty in a variety of complex, natural, and engineered systems. His research focuses on three main areas. First, advanced Bayesian nonparametric regression methods for surrogate modeling. Second, Bayesian integration of empirical data, simulations, and expert judgment for uncertainty-aware prediction and inference. And lastly, sensitivity analysis for complex systems of models. Today, Dr. Francom will be presenting Getting the Most Out of Sensitivity Analysis, a brief review of practical approaches. In his talk, he will provide an overview and demonstrate a collection of approaches to sensitivity analysis, including variance-based sensitivity, emulator-based approaches, and design of experiments approaches, just to name a few examples. Using the Preston-Tonks-Wallace strength model as an example, he will highlight what insights can be gained at different levels of computational effort and how these analyses can uncover important effects even when treating a model as a black box. And with that, I will stop sharing my screen and hand it over to Dr. Francom to get started.
All right. Thank you, Elise. All right. I'm excited to be here with you. I am a big fan of SDNS, and this is joint work with Abby Knoxine from our group at Los Alamos also. What I mean by sensitivity analysis is, we do this all the time. We want to understand how, if we change some input to a model or to some system, how it will change the response. And so Saltelli's definition is a little more specific. Sensitivity analysis is the study of how the uncertainty in the output of a mathematical model or system can be apportioned to different sources of uncertainty in its inputs. And that might be familiar to many of you because it has a feel like ANOVA, analysis of variance, the way that Saltelli put it here, apportioning uncertainty in outputs as due to uncertainty in inputs. Remember in ANOVA, like your sum of squares for each effect, for each variable, if you're familiar with that. Okay, so why would we want to do this? The reasons that I've seen discussed, one is to understand robustness. So robustness being, if we have things that we're uncertain about that are inputs to a model, we want to understand whether those are causing a lot of variation in the response of our model. And similarly, if we want to reduce variation in the response, we can prioritize which inputs we need to go after to reduce variation of those inputs in order to reduce uncertainty in the response. And okay, so I talked about inputs and outputs, or inputs and response here, but a number of us have been trained up in thinking about sensitivity analysis more broadly. You think about, as a statistician, the assumptions you make in your model, or if you're doing a Bayesian model, what priors you choose. We're encouraged often to, or we want to often perform sensitivity analyses to see how sensitive we are to those particular choices. But a lot of what I'm going to talk about today is more geared toward physical models, though you could apply it to statistical models. Physical models and mathematical models that, like, think systems of partial differential equations or things like that are used for modern scientific exploration. So, understanding robustness and reducing uncertainty in the response by going after uncertainty in the inputs, maybe that looks like, there's some measurement of some quantity that's an input to our model, and we have some uncertainty from that measurement. And if that measurement uncertainty is driving a lot of uncertainty in the response, like too much for us to be able to make good decisions with this model, then maybe we can go after reducing the uncertainty in that measurement as our way to be able to use the model to make decisions. So that's kind of understanding robustness, prioritizing, reducing variation. The other kind of why we would do this, understanding relationships between inputs and outputs, as well as searching for model form errors and communicating with decision makers. Those are all related to interpretability in my mind. And sensitivity analysis can be used as a tool for understanding, interpretive, or explaining what's happening in our models. So if we can understand what the effect of one of the variables is, or a collection of variables, that can help us. Well, if we don't think that effect looks right, and it's hard to look at some complicated models, partial differential equations, or complex computer models, and see explicitly what the effect of changing one variable across some range is. And so if we can do that, we might be able to look for model form errors better. And those kinds of things are also, because of the interpretability, very useful to decision makers. We can think about fixing inputs that make no difference. We work with a lot of high dimensional models at Los Alamos, thousands of inputs. If actually there's, 10 underlying inputs that are important, then it's really valuable to know what those are so we can better design model runs that explore those variations. And we could do it much more cheaply if we know there's only 10 active dimensions rather than 1,000. Yeah, okay, so related areas are things like uncertainty analysis. That's largely used in engineering style problems and kind of discussed in the VV-UQ world, verification, validation, and UQ world. And that's dominated by engineering fields. And that's largely interested in kind of forward propagation of uncertainty. So sensitivity analysis is going to take that one step further to forward propagate and then say why you have that uncertainty that you have and how you got it, where it came from. And then design of experiments is very related also. And the more I learn about design of experiments, the more I feel like there's a lot of really cool stuff there. But it's really geared toward expensive experiments that you can do very few of. And so you have to get the most information you can out of a limited number of experiments. Sensitivity analysis, we'll see that we're not always that constrained and stuck with such a small number of model evaluations. Okay, so one thing I want to emphasize is that sensitivity analysis, like I'm talking about, is a field of research, and there's a lot of good reviews out there. Andre Saltelli, that I just mentioned, this is a book that I think is a great resource. And these two papers are great review papers that have some of the more modern approaches that are being used. There's also some great open source software. The R package sensitivity is a great one. That one has a lot of, as new methods are developed, they will end up there. And so there's a lot of different methods that can be tested with that package. In Python, the SALib module is kind of an up and coming module for doing similar things in Python. There's a lot of resources in MATLAB. UQ Lab from ETH Zurich is a great resource. And some other resources out there, OpenTurns. I'm guessing Dakota has some capability, Dakota from Sandia. All right, so we mentioned that I'm going to explore sensitivity, and I'm going to show you on a test model. So this is the Preston-Tonks-Wallace strength model. So this model, you have a set of 10 input parameters that are specific to a particular material. So this is to characterize strength of a typically metal. And so if you pass these 10 parameters, you can get stress as a function of strain, strain rate, and temperature. For the purposes of this talk, I'm going to simplify to a scalar response instead of that kind of functional response. I'll fix strain, strain rate, and temperature at particular values that are interesting. And that's realistic. And a lot of sensitivity analysis and modeling scenarios will do analyses on scalars before we go to more complicated scenarios. So I'm going to treat this as I have 10 inputs and a scalar response. The 10 inputs, they're physically motivated. They don't necessarily have physical interpretation. And then I'm going to rescale those so that they live on the unit hypercube. So they're all kind of meaningful between 0 and 1. And also I'm going to assume they're independent here, which I had to make some simplifications to the space I'm working with to make that true for this PTW model, but we'll discuss kind of how we can relax that later on. But this is a realistic scenario for many models that you have a collection of independent inputs on the order of 10, and you're interested in some scalar response and understanding how uncertainty in these inputs is influencing uncertainty in the response. Okay, so first, this is a list of potential methods. It's not all the methods that exist. It's a smattering of potential approaches that cover some kind of dimensions of what's possible in sensitivity analysis. So some common concepts that will be used throughout. I'm going to go through almost all of them individually and demonstrate what it looks like for PTW. And we'll talk about a function f of x, and that's going to be PTW. So x is 10-dimensional input, and f of x is the scalar response. It's PTW stress at those particular parameters I mentioned. We're going to see the concept of partial derivative and gradient as being kind of key concepts for a number of these methods. In fact, in a lot of the physical sciences, where those fields will learn about sensitivity analysis, it will be almost synonymous with gradient. And we'll describe what that gets you and what it doesn't necessarily get you. And then what's kind of the interesting approach that kind of probability theory version of this brings you, if we think about x, the inputs, the 10-dimensional inputs, as random variables, a vector of random variables, then we can talk about, we think about them as random variables as we have uncertainty about them, and we can characterize that uncertainty in a probability density function or something. And so that this pi of x, we're going to talk about as the probability density function for x. And then we can talk about expectation and variance. And also, this will be a key, that this idea of f of x, we just think about that as a transformation of random variables. And so that is also a random variable. And we can talk about expectation and variance of f of x. Okay, so let's jump into, let's say you can do as many model runs as you want. You can do millions, billions of model evaluations of f of x at different x's. What could you do with that? And I'm going to go through kind of, if you could do as many model runs as you want, or if you're in a more limited scenario, or if you're in an extremely limited scenario, and how we'll approach each of those for learning whatever we can about what our model is sensitive to. All right, so I'm going to start by discussing the Sobol decomposition and the things to know about it. It's really kind of the workhorse of global sensitivity analysis. Global meaning is considering our uncertainty over the whole range of inputs, not localized to a certain input location, like using the gradient would be. The gradient is based on, it slopes at a particular location in the input space, where the Sobol decomposition and global sensitivity approaches in general are going to be thinking about the entire input distribution of potential values. So Sobol is going to be the kind of extension of ANOVA, analysis of variance, to more arbitrary models. So ANOVA is limited to linear models, and so this is going to be for nonlinear models. And we know ANOVA is powerful, so this is going to have the same powerful interpretation. We're going to talk about proportion of variance explained by different inputs. The problems we'll see with Sobol, the Sobol decomposition, is that there's that estimating this decomposition can be difficult. That it's focused on variance, and sometimes variance isn't the greatest description of our uncertainty, and it's going to require independent inputs. Okay, so at the kind of the basis of the Sobol decomposition is the functional ANOVA decomposition, and this has been used in statistics for a long time. And the idea is that our function f of x, which is PTW for us, we're going to decompose into an overall mean plus main effects. So these are effects of one variable at a time, and they're of arbitrary. They could be nonlinear. and then two-way interactions, so functions of two variables at a time, and so on. Three variables at a time, four variables, all the way up to like the 10-way interaction. And so how do we come up with these functions? How do we get these? Well, we're going to define them in a specific way. So all based on conditional expectation. And remember, our inputs are independent. The F0, that's going to be the overall mean, the expectation of f of x, so not conditional on anything. And then Fi of xi, that's the effect of the ith variable, the main effect of the ith variable. That is the expectation of f of x, where xi in there is fixed at a certain value, xi. And so, that will be different depending on the value of xi that xi is fixed at. So that is a function of this xi. And then we're also going to subtract the overall mean. And then a two-way interaction, we're going to, it's another conditional expectation where we have xi and xj now. So that's a function of two variables. It's averaged over everything else than these two variables, but it's different depending on where you are in those two variables. And then we're also going to subtract out the lower order effects, the main effects in this case, and the overall mean. And, the three-way interactions are defined similarly, subtracting off all the lower order effects, and so on. And if we construct these terms in this way, they are zero-centered because we subtracted off all these things, and they're orthogonal, exercise left to the reader, and they are unique. So now, just to demonstrate what those effects look like, these are for our 10 variables in PTW. I am showing the value of that variable and the effect, like Fi of xi, right? So for x6, that's this purple line right here. That's the effect of x6. As you increase x6, you get a smaller value of f of x, of the response. And as you increase x3, you get a larger value of f of x. And so, okay, so this is just the effects. It's already an interesting thing, right? We can see x6 is a dominant player here. If we have uncertainty over this unit hypercube, and we can see which direction the effects go. We can also see interaction effects. So this is the 3-6 interaction. And we see at particular extremes, we see, interaction effects. This is, now remember the definition, how I built these effects is that they were sequential. So these have the main effects subtracted out. If I added those back in, this is what the 3-6 effect looks like. So I just added in the main effects. And so already some interesting things we're able to get out of this. So this is the effect after we've marginalized over all the other variables. Okay, so here's where the magic happens. If you take this functional ANOVA decomposition with these effects that I just made in the last couple slides, in the way that we made them, the conditional expectations. Now, I'm going to turn this into a variance decomposition. I'm going to square both sides. Okay, if I square the right side, okay, the left side, square that, it's f squared of x. The right side, this huge sum, like there's a crazy number of terms that are going to expand out when I square that whole thing. But if I then take the expectation of both sides, I get the expected value of f squared of x on the left. And then all the cross product terms or cross terms, when I squared this sum, they'll have expectation 0 because these terms are orthogonal. And so I'm just left with these, with the terms I had before, but expected value of the squared effects. Okay, so then I'm going to use my favorite, identity from relating expectations and variances right here. So this is the variance of a random variable equals the expected value of the squared random variable minus the squared expectation of the random variable. And so if I move this, this is the squared expectation of f of x. If I move that to this side, then I have this term, which is the variance of f of x. So that's down here. If I then look at this, these terms were zero-centered, which means their squared expectation is zero. I'm sorry, yeah, their squared expectation is zero. So that means these are also variances. So that's how I get to this variance decomposition. The total variance of the function is equal to the sum of and remember, when I talk about the variance of the function, I'm talking about x was a random variable. I did a transformation, f of x. And so that's a new random variable. And I'm talking about the variance of that random variable. And so that is the sum of the variances of the conditional expectation terms for the main effects. So the variance due to each main effect, variance due to each two-way interaction, and so on. And okay, so these terms throughout, I'll call those the variance of the conditional expectation. Okay, so then that's already a powerful thing that we have here. We decomposed the variance. We only had to make the assumptions of independence of inputs, and we're assuming that variance is a good summary of uncertainty here also. So there's not heavier tails or skewness or things like that, or multimodality. But in that case, let's think about now if we divide both sides of this by the total variance, so that we have 1 equals the sum of the proportion variance explained by each main effect plus the proportion variance explained by each two-way interaction, and so on. And that's the Sobol sensitivity. That's powerful. We have, for x3, for example, what proportion of variance of the response that is explaining on its own and interactions. And sometimes we're interested in just having a single index summary of sensitivity. The total Sobol index is to take each of these Sobol indices that involve a certain variable. Like if we're talking about x3, we'll take the main effect for x3 and all the interactions that include x3 and add them together. That's the total effect. So one downside of that is it kind of overcounts or is just allowing interactions to be counted equally to all variables that are involved. We'll talk about ways that we get a little bit better of a portioning of interactions to their sources in a moment. But another way to think about total index for Sobol is the expected remaining variance when in f of x when the inputs other than I are fixed or known. All right, so that's all well and good. This is a cool decomposition, but we had to do a lot of expectations and variances, which are integrals, to get here. And so how do we actually estimate these things? There's many Monte Carlo approaches. Many of them are around this pick freeze approach, it's called. I won't go into that, but it's essentially that you can estimate the variance of the conditional expectation by taking the covariance of two sets of evaluations of the function if you do it in a smart way. And so that's why in a lot of the code to do or software to do this, you'll pass two designs of model runs, like a X and a X prime, and under the hood, it's going to take different for each vector of indices U, which are a subset of the P variables. It's going to do this fancy pick freeze thing to get at this estimator. And it's actually pretty simple. It's a thing you could code up in a few lines. Another approach that's often used is Fourier amplitude sensitivity test, or FAST. It uses a neat little transformation to get these high dimensional integrals down to lower dimensional integrals in Fourier space. And that has actually been around a long time also, since the 70s. All right, so for PTW, let's say I do this with PTW and I have to decide how many model runs I'm going to go after. This is showing from a collection of methods that are available or functions in the R package sensitivity, what you get in I guess error in our sensitivity indices. So the y-axis is error in the sensitivity indices, the Sobol indices, in log 10 RMSE. And then the x-axis is number of evaluations of the function. So with 1,000 evaluations of the function, log 10 RMSE of 1 or -1, that's saying we have like a 0.1 RMSE, which is large, right? That when you're talking about indices that are between 0 and 1, a 0.1 RMSE is pretty large. But so think of this axis as like how many decimals of error, I guess. And so you see as you increase the number of evaluations of the function, you can get more accurate. And notable things here, this top one is for main effects, and this one, bottom one, is for total effects for Sobol. And you see that this fast approach, the Fourier amplitude sensitivity test, starts converging to smaller error much sooner. And that's not just the case with PTW. I think that's pretty common. It's at least that's the case for the main effects. It's a little bit less the case for the total effects. All right, so now you can see, these are ways you can go about the estimation of these Sobol sensitivity indices. Another interesting extension of the Sobol sensitivity indices, and also we'll see this for many other sensitivity approaches, is that we can talk about subsets of indices kind of going together. So why you would want to do this, like a lot of the computer models I work with, for instance, are made up of many submodels, and each submodel has, like PTW could be one of the submodels, and there's 8 submodels, and PTW has 10 parameters, and each of the others has a different number of parameters. And really, what I'm after is not the individual effect of parameters, but the effect of a submodel and how much variance that submodel is driving, so that I can, I can prioritize research. If it's like for a particular material, that submodel, I can say, if that's explaining a lot of the variance, I need to go understand that material better. Not a particular parameter necessarily, but I just need more experiments to probe that material. And so it looks very much the same as the functional ANOVA before. It's just that instead of individual variables, you have subsets of variables, and the variables 1 through P are broken into some subsets, some partition of 1 through P. And we still have the case that the subsets of variables across subsets are independent. Although in this case, we can have dependence within a subset of variables. So that's another place where it's powerful. If I have, submodels that have dependent inputs within, but independent variables across, I can still use this subset version of the Sobol sensitivity. Okay, so that's another useful thing to have in your back pocket as a sensitivity practitioner. Shapley values is the next thing we'll discuss. And don't worry, I'm not going to go through all of these in that kind of detail. The Sobol sensitivity is really a powerhouse in this field, so it deserves a bit more time. The Shapley values, at least in the way that I'll describe them, build on the Sobol sensitivity. They can allow for dependent inputs. However, it's still a kind of open research into the computation for these. There's some difficulty there, and they have a bit more complicated of an interpretation. So to explain what the Shapley values are, it's a game theoretic idea of understanding how much value a player brings to a game that involves teams or groups of players. And so the concept we'll have here, the value of so here J, capital J, is a subset of 1 to P, subset of the parameters. And I want to consider the value of that team of, okay, so the notion of a team and a game, we're going to replace with variables and a function. So the team of players is like the collection of variables that are used to explain some response here. So the value in the game theory approach, the value of players in a subset J that doesn't include player I versus the value of that subset when it has I added to it. And so the idea is I'll do that for every choice of J, for every set or subset of 1 to P without I, and say how much does variable I add if in value if it's included in any other subset of variables. Now, what do we choose for this value function? Well, really interesting work pointed to let's use the variance of the conditional expectation from functional ANOVA. And so the value of a set of parameters J is the variance of the conditional expectation conditioned on those X's J that are in the subset J. And you may have also heard about SHAP in the machine learning world since like 2017, although maybe it's fallen out of favor. It's hard to keep up with that world. The idea of SHAP is instead of this definition of the value of some set of inputs, they will define it as just the conditional expectation. And so then you can think about it locally instead of taking the variance over that. Okay, so Shapley is a cool approach. I'll show you that compared to Sobol for PTW in a minute. But first, I'm going to talk about a couple more approaches that we'll compare all of them at the same time. This delta, or the indices that we'll call delta indices or moment-free sensitivity, these are, the way that we talked about Sobol was very variance-based, variance of the conditional expectation. And the way that we talked about Shapley was also based on the variance of the conditional expectation. But what if variance isn't a great metric for uncertainty in your case, like if you have multimodality or things like that? This is going to extend these kind of ideas to this moment-free approach. So instead of the second moment variance being the key spot, we'll use the whole distribution. It has some other advantages that I'll talk about. The disadvantages, it's a little more complicated of an interpretation than Sobol, at least, and it's going to require a lot of model runs to estimate. So let's get into it. So we said functional ANOVA was variance centric. What if I take f of x, I say that's a random variable called y, and that y has a distribution g. So the PDF G of y is the PDF of y. So this is for PTW. This black curve here is the PDF of y here. So if I allow all these inputs to vary on the unit hypercube, this is the uncertainty I get in stress for PTW. What if, though, I fixed one of the inputs at a particular value? So if I fixed x3 at 0.75, well, then if I take the distribution of that random variable where I've fixed I'm letting everything else vary, but I'm fixing x3 at 0.75, this is the density of that random variable in red here. In gray is the difference between them highlighted. And so the notion of this metric is to get the difference between this, and so that's this integral right here is the gray area, this inner integral, and then to take the expectation over different values of x, or expectation over x. And just to give you a sense of what that looks like for x3, I've fixed it at 0.75 here. That's like one of these curves right here. If I fix it at 0.01, this is what the density g of y looks like. If I fix it at 0.99, this is what the density looks like, g of y. And, all of these values in between are, the values of x3 in between 0.01 and 0.99. And so you get a sense of what this metric is after. It's saying for each of these, I'm going to look at the deviation between that and this dotted line, the one that was not conditional on fixing x3 on something. And if I see that fixing x3 at different values is vastly changing the distribution of the response, then I know x3 is influential. And so taking an expectation over those finishes that. So some of the nice properties, I think one of the most important ones is that this is invariant under monotone transformations. So if I were to transform f of x or y, this comes up a lot when I have, I want things to be positive and I want to make sure that I keep things positive. So maybe I consider the log of y. And if I were to do the Sobol decomposition with the log of the response instead of the original response, well, I could get a pretty different Sobol decomposition. Under this approach, this is going to be the same under a monotone transformation like this. Okay, another thing you might be thinking is, oh, well, difference between densities, that's also natural to think about with something like Kullback-Leibler. And you can do that here. The authors, the people that developed this have shown some cool approaches using that kind of approach. So Borgonovo and company have done a lot with that. All right, so what does it look like for some of our PTW inputs? So x1, x3, what you're seeing like x1, as you change x1 and fix it at different values, the density of the response doesn't change a whole lot, right? Compared to x3, x8, it doesn't change at all. So we can see x8 isn't really getting used. x6, it changes a lot, right? The differences between these lines as we've fixed x6 at different values and the dotted line here are pretty different. x7, you see something interesting. You see this like extra peakedness, but the same tail. And so if you were to compare this, so what this is showing up here, I used the Python package salib, and I used it with PTW, and it gives me the delta indices, and the main effect for Sobol also is shown. And so the Sobol main effect is pointing to x6 being the key player, and then x3, and then maybe x7. But this delta approach is showing x6 being the main player, but then x7. And that's because variance right here in x7 isn't necessarily changing as much as the density because of this high kind of peakedness that shows up. The variance doesn't change as much as the shape of the density changes. And so that's why this one is registering x7 as something that's more sensitive to than Sobol is. Now, I should also say that when you do this in salib or other software, there's approaches to sensitivity analysis that are often called like given data, meaning you have a set of model runs and you're trying to do sensitivity analysis with it. And this, what I'm showing in blue up here, was the salib approach in this given data scenario. And what it's showing, like, for instance, it's showing something for x8. And I know there shouldn't be anything for x8. And this is because this is an artifact of this given data approach. If I do it on my own and just go crazy with the number of model runs, I can get like x8 to have 0 as that delta index.
Hey, Devin,
Yeah.
we have a question from the audience.
All right.
So the question is, does a difference in one direction, decrease in density, have a different interpretation in terms of sensitivity than a difference in the other direction, increase in density?
Yeah, I think under the way that I've defined it here, it doesn't, right? I'm saying a difference, if I go back here, like this difference and this difference are just added together, like, or integrated together, right? So I'm not getting any specific information about density one way or the other. You could probably define a metric um, that emphasizes one or the other if you're interested in that, but I am also not sure kind of what the utility of that would be. I guess if you look at this, for example, this is showing different values of X7 will basically rule out some of these lower values of Y, right? Uh, and so I guess that's the way to think about density here is lower values of density, meaning like we're going to get rid of those settings of the response versus higher values of densities, like we're going to have more of those. And I haven't seen necessarily where people have used more specific metrics to emphasize one or the other. Are there other questions at this point?
No other questions, but thank you for,
All
for
right.
your response.
Yeah. Okay, we're going to change gears again and go to another approach, active subspace approach. Uh, and it's related to a couple others on here. It can handle dependent inputs, though its interpretation is not so clear. It's a little more complicated of an interpretation. And in fact, I think there's been some really interesting work to connect it to the Sobol decomposition. But the only way it can really be connected is through a bounding argument rather than something more interpretable than that. So let me explain what I mean by that. So the active subspace it's typically used for dimension reduction for a computer model or a model. So if I have my model f of x and I get the gradient of f of x and take the outer product of the gradient with itself, so that makes a matrix, right? This is a p by p matrix right here. P is the number of inputs. And then I have pi of x here. I'm taking the expectation of this matrix. And and then if I further decompose that with the eigen decomposition, uh, the active subspace is like the eigenvectors that go with the dominant eigenvalues in that eigen decomposition. And it can be really powerful for finding a lower dimensional subspace where your model is really active. And it's a projection of your inputs down to a lower dimensional subspace. So it's a linear projection, but yeah, there's a lot of really interesting use cases of this kind of thing. What a lot of authors of work in that area, Paul Constantine and company, have pointed to is sensitivity metrics like using just the first eigenvector, the largest eigenvalue eigenvector as a mechanism for sensitivity, right? That's a projection, so it kind of makes sense as a metric for sensitivity, probably the absolute value of it. And then activity scores are a linear combination, combined by the eigenvalue and with squared eigenvectors. So taking all the eigenvectors and weighting them by their eigenvalues. Okay, so I believe I'll show an example of this in a moment. But okay, this is where I'm going to change gears a little more and think about what if you can't do all the model runs in the world that you ever wanted, billions and billions to do this. You could only do a smaller set. And at the end we'll get to, you can only do very small set, like tens. This, I'm thinking more like hundreds or thousands, which we find ourselves in that position a lot. And what I'm going to say is that a key approach here is to use the model runs to build an emulator or a statistical surrogate model, a fast statistical surrogate model that you could then arbitrarily, predict at new settings or interpolate between, your model runs. And so if you could only do 1,000 PTW runs, well, you could build a model that from those 1,000 could predict at any, interpolation between them. And so people often use Gaussian processes and polynomial chaos, splines, trees, things like this, people use random forests and neural networks. Basically, all the machine learning world is open to you. But there are fewer of these approaches that have some value, especially in sensitivity analysis. And I'm going to talk about one of them, but the things to know, like polynomial chaos, for instance, has closed form Sobol indices. So does BART, Bayesian additive regression trees. And so does this approach I'm going to show, Bayesian Mars, or Mars is multivariate adaptive regression splines. The software to do Bayesian Mars is called BAS, Bayesian Adaptive Spline Surfaces. And there's an R package, BAS, a Python package, PyBAS. I'm going to talk about this one because it's the one I've done more work on. And okay, so I mentioned you can get the Sobol decomposition in closed form for particular choices of input distributions, like uniform or normal or mixture of normal. You can do this. So it gets pretty flexible with mixture of normals. And there's also Monte Carlo approaches that can get you a little more flexibility at the expense of some Monte Carlo error, but not the full Monte Carlo error that we'd use as if you were treating these like a black box. So what you're seeing here is the various inputs to and interactions and so forth. And you can get the full Sobol decomposition, not just main effects and total effects. You can get all the interactions. And so that's a valuable thing about these approaches with closed form Sobol decomposition is that oftentimes you'll be able to get the full Sobol decomposition. So we can see from this that there is a 3-6 interaction right here. And there's also a 6-7 interaction. And so those kinds of insights are valuable for modelers and for various purposes. So the problem, though, if you're going to use an emulator to do and just use that in place of your computer model and do sensitivity analysis and make judgments and decisions, well, your emulator better be pretty accurate, right? And so when you're fitting an emulator, you can get the residual error. So this is showing the residual error for this PTW model with this BAS emulator. And then I can take this residual variance and show it. If I took my Sobol decomposition and went and transformed it to variance explained instead of percent variance explained, then I can look at that compared to my emulator residual variance. And that's this line here is the emulator residual variance. So you see the X6 effect, the 3-6 interaction, the 6-7 interaction, the 7 and the 1 effects. And you can see that the emulator error is such that you probably shouldn't try to overinterpret things that are smaller than that. And there's probably like some cool F-test that one could come up with to think about when you should consider an effect significant, but I'm not really that kind of guy that could come up with that F-test. I'm more of on the Bayesian side. So anyway, that's a thing that I haven't seen done, but if you're into that sort of thing, you could probably pursue that. Okay, we could do we could build an emulator. We could get at sensitivity through the emulator. I should also mention, like I talked about Shapley values, and I talked about active subspaces. Those are also closed form with BAS, Shapley values and active subspaces. And so that's pretty powerful. I should say the Shapley values with independent inputs are closed form, but we haven't worked it out with dependent inputs yet. And the active subspace stuff, there's been a lot of cool work. I think Kellen Rumsey is on this call, and he's done a lot of really cool work with if you can get the active subspace in closed form with BAS, there's a lot of really cool analyses you could do with it, including coactive subspaces and things like that. All right, so moving on to what if you could only do very few model runs? And the first thing I'll talk about is the DGSM, the derivative-based global sensitivity metric. It's built for very small model run settings, and it's also connected theoretically as a bound for the Sobol decomposition. And I'll particularly talk about as an upper bound. I think some of the cons associated with it is that it's distribution dependent, and it's hard math for coming up with the bounds. And the fact that it's only a bound means it has some limitations in our interpretability. So the idea is we take the partial of f of x by xi, square it, and take the expectation. So you could think of this as you go to a bunch of different spots in your input space and get the partial derivative of the function with respect to xi at those places and square them and take the average of those. And there's also a version where you don't square them, and there's kind of different theory for why you would do each. It's related to something called the Morris method that I'll talk about in a minute also. But there's also the relation to the Sobol sensitivity that's been explored in a number of papers. So just to show you, this is where I'm going to show you. We did for PTW, we did the Sobol index, the main effects in blue here, and the total effects in orange, and the Shapley effects are in between them. That's actually for independent inputs. That's the case. It's provably the case that the Shapley values will be between those two. But they're kind of a better balancing of how interactions should be accounted for than what the Sobol total effects do. And then the DGSM bound, this derivative-based global sensitivity metric I was just talking about, that upper bound is shown here in this color. And then that delta approach with the moment-free approach is shown in dark gray. And so you can see that for these different inputs and see the value that you're getting from these. So you can see, like with the DGSMs, you could say, okay, we definitely can't rule out that X6 has a large effect. And I think there's DGSMs for lower bounds also that can be, I think, also calculated, but maybe are a bit more tricky. But with the upper bound, what you can rule out is that there's a variable 2 effect or a 4 effect or an 8 effect. And so that's pretty powerful. And you could do that with very few model runs. Okay, so some other things. We already talked about how the delta approach, like we sometimes get some differences with Sobol. But over here, you also see the Sobol effects in black for 4 different variables here, 3, 6, 7, and 9. And you see there's something called accumulated local effects that we're not going to talk about, but that's another approach to getting effects. And you could think of it as a way to approach sensitivity also. Those effects are shown in green, and so you see some similarities there. And then the colorful points here are from SHAP, that machine learning Shapley values approach, where the value function is the conditional expectation rather than the variance of the conditional expectation. And you can see that those are pointing to similar effects. The SHAP values are colored by the value of another parameter of X6, as you can see by the color there. So you can see a 3-6 interaction effect kind of with those SHAP values. Anyway, so this is just demonstrating the kinds of things altogether that if you had done one of these, like oftentimes people just do one of these for sensitivity, but you could consider what you could learn from various ones. Another approach, and I think I'm nearly to the end here. So the Morris method, this is from Max Morris, early 90s, and from a design of experiments standpoint, and it's a pretty neat approach. Few model runs. I'll show you what it looks like here. the idea is basically, and the derivative-based global sensitivity metric, I think, was inspired by this. So the idea is taking the gradient at a bunch of points in the input space and averaging the partials and getting the standard deviation of the partials. So if you look at, so mu is the average of the partials, sigma is the standard deviation of the partials, and the partials are, for the various inputs. So the X6 partials tend to have, tend to be, up to, 0.017 or something like that, and have standard deviation of 0.01. So they can vary quite a bit and are large with respect to the kind of variance that we have in PTW. And so basically the idea is that if you had a large mu and a small sigma, that would be indicative of linearity. And that means, right, if you have a large mu and a small sigma, it means your partials are very similar and non-zero. And if the partials are all the same, it's totally linear. Okay, and then if you have sigma larger than 0, it means you're seeing nonlinearities and interactions at play. The cool thing about this, because it was built from the design of experiments perspective, you could do it in very few model runs if you carefully choose those model runs. Particularly 4P is what was suggested in the Max Morris paper here. What I would say is the con is stability, and I'll show you. So what I was showing on the previous slide, the black points here, that was with 4,000 model runs. So I calculated those collection of partials with 4,000 model runs. If I only did 40 model runs, which is the suggestion, 4P, I could get kind of some switching of orders of importance of variables. And this is showing I did it 10 times with a different, random seed when I'm doing these specially chosen 40 model runs. And I can get this kind of variation. So, but that was kind of, I think the idea when it was developed is that it would be a preliminary tool for screening style investigations. Okay, so now finally getting into, if you just used what would be more modern design of experiments approaches, what you could do. So very few model runs, they're always designed that way. It gets complicated for input dependence, and particularly like it has kind of a response surface feel. There's linearity or near linearity often assumed, and so nonlinearity, we have to just be a little careful with that. But I find that in a lot of cases, linearity is not a terrible assumption to start exploring things with. So definitive screening designs is particularly what I'm going to talk about. It's a class of screening designs. Let me just skip that one. So there's 3 levels. There's for each input. There's a high, medium, low. And they're basically definitive screening designs are constructed from these conference matrices, and these are. I won't go into the details of what conference matrices are, but the idea is that it requires very few model runs. 2P plus 1 is one suggestion. Another suggestion is 2P plus 5, which is what we used here. And this is what the design looks like. Low, medium, high, we're doing it as -1, 0, 1, which then we rescale to the 0, 1 hypercube. But this is 25 settings that will run PTW at. And this is showing what our what kind of main effects we get. The idea of these definitive screening designs is that we can get the main effects, the pure quadratic effects, and the two-way interactions that are at play, assuming that there's some sparsity of these things. And so these runs are designed very specially to be able to infer those. And we get, similar to what we've been seeing, like if I look at the T statistic here, like X6, or look at the effects over here, like X6 is the big player, and then X3, and we see, X7 having some influence, and then we can see interactions like the the 3-6 interaction as being a big player, and the 6-7 interaction shows up also. And this quadratic effect for X6. So that's pretty cool, right? With just 25 model runs, we could discover a lot. And I think we would generally suggest that in expensive computer model settings, that it's good to start with that sort of thing and do some extra model runs to explore whether you have violations of the assumptions of this kind of fit, like if you have more extreme nonlinearity or higher order interactions. All right, so conclusion. There's many different sensitivity approaches. They all can rank inputs for you. Some can quantify interactions. Some have can handle input dependence. They all can have different interpretability and be useful in different ways. I can get into some of the complicating factors like functional response and some of the more complicated parts of input dependence. And also, there's a world of kind of second level sensitivity of like how sensitive is my sensitivity analysis to my input distribution choices. And all those are active areas of research. I find that if I can afford enough model runs to build an accurate emulator, I can usually do a lot of really cool stuff with sensitivity analyses there. And then, if you're really limited, you want to build on maybe some of these design of experiment ideas. All right, and that is all I have.
Thank you for a very nice presentation. How do these methods deal with hierarchical data structures? For example, blocks, nested effects, split plots.
Yeah, that's a good question. I'm not really a design of experiments expert, but from the sensitivity analysis perspective, like Sobol decomposition, for instance, there's typically not a notion of blocks or things like that. Or if there is something like that, it's set up through dependence, right? So if we're going to consider the inputs as random variables, we're going to capture everything about those, how those random variables can vary together in the probability density function, their joint probability density function. And if that has structure, yeah, maybe there's certain things we would want to do differently. But I haven't necessarily seen where people have done anything quite like blocks or stuff like that. I guess we would, if we were just going to discover that, I think we would discover it as like in the Sobol decomposition, we would just see that some effects are nested in that way. Not sure if that made sense.
Nora, are you still on the line? Hopefully that answered your question.
Thank you. Thanks for the response. When dealing with hierarchical data architecture, what happens is that you're basically dealing with different amount of uncertainty on different factors being evaluated, right? If there's data architecture, it's often the case that factors might have different sizes of experimental units, and therefore different error terms and different standard errors, which complicates the assessment of sensitivity because the baseline uncertainty is not the same, so the evaluation of the magnitude of the effect and the sensitivity is also different. That is what I was trying to get at with my question. Is it appropriate to assume that the methods you've discussed here are methods that deal with a single source of non-systematic random variance?
Well, okay, so if the factors have different scales and
Right.
so if we're going to capture that, we would capture, okay, we want to capture their, how, how they should occur in probability density functions, right? So, and then everything is based on that afterwards for something like Sobol or these variance-based approaches. And so then it doesn't matter that they have different scales because we're
Sorry.
just interested in how they influence the response.
I understand. This is not about the scale of the factors. Let's say that all the factors are put all on the same scale and standardized before even starting. If you have a hierarchical structure, if it's possible, it's quite likely actually, is the definition of hierarchical structure. Different factors will have different sizes of experimental units, so different error terms, different standard errors, different, and that is the piece that I'm asking about here. And I'm sorry if I'm being too insistent on it. It's we
I
deal with
think this sounds interesting. But I don't know that I necessarily understand it. So when you say different levels of experimental error, are you talking about of the factor itself or of its influence on the response?
So think of it as in terms of an ANOVA, like you were explaining the analogy between Sobol and an ANOVA approach, right? The decomposition of variances. When you think of a standard ANOVA, your residual is your only source of random noise, and everything is compared against what's happening at the residual level. Against your F-test statistics go back to the mean square error. When you're dealing with hierarchical structure, that's not necessarily the case. Error terms for factors of interest might be a function of the residual variance and something else. Those are the types of cases that I'm referring to, and maybe this is an issue of different types of applications. This type of hierarchical data structures are very common in agriculture. I'm not sure how they apply to physical settings like the one that
Yeah. Okay, I think there's probably something really interesting there. But in general, I think the sensitivity analysis world for like computer experiments and computer models, the relationship with ANOVA there breaks down a little bit in that we don't have residual error in those in our physical modeling setting or our computer modeling setting. We had it technically when we were using an emulator, but I don't think that has actually been treated specifically. At least I don't know of any cases where that's been treated as part of the sensitivity analysis in this literature. But yeah, I bet there's something cool there.
You did mention at the beginning of the talk that your focus was going to be on mathematical models, physical models. So I'm probably off base here. But I appreciate it was a very good presentation, lots of details, good details and method comparisons. So thank you.
Thanks. Yeah, I would say one more so where we are often thinking about deterministic mathematical models. There has been some interest in stochastic computer models for sensitivity analysis and like Sobol decompositions. And one version of that I've seen of that, for example, but it's still very much in the kind of computer model realm, is if we can do Sobol sensitivity for quantiles of a response. That's something that's out there. But it's a little harder to really relate that to something like agricultural settings where you just have measurement uncertainty for or stochasticity that's not the mathematical. Anyway, yeah, I think there's probably some interesting work there. I think I would love to see more collaborations between the sensitivity analysis crowd and the design of experiments crowd, just because I think there's a lot of shared interests.
Absolutely, and many factors are evaluated in other disciplines too. So the concept of sensitivity analysis is most relevant. Thank you again.
I know you said you're attending JSM. Are you presenting at JSM?
Yeah, on the computer model calibration there. So,
okay. We'll keep an
but
eye out for that on
all right,
when they
yeah,
send out the program.
okay. All right, thanks everyone.
All right, thank you so much, Devin. Thanks for taking the time to share your research and to demo a variety of sensitivity analyses with the SDNS and ASA communities. Before we wrap up, I do have a few announcements for everyone. If you would like to connect with Devin after today, you can reach him by email as listed here on this slide. If you are interested in presenting at a future webinar, we'd love to hear from you. You can visit the SDNS community website or email me at sdns.amstat@gmail.com. And lastly, I'd like to thank all of you for attending today's webinar. Have a great rest of your day.